Welcome back to CS 520. In this session I want to talk about garbage collection. So what is a garbage collector? Well, it works with a memory allocator, and the idea is it identifies allocated blocks that are garbage. In other words, allocated blocks that can be reclaimed and reallocated. So it frees the programmer from having to use a facility to explicitly free blocks. Let's start out by looking at a memory allocator first of all. So by a memory allocator I mean some set of functions with these kinds of interfaces. There's some way to initialize a heap where the programmer provides a heap size, and then there's ways to allocate blocks out of that heap by providing a block size. And in this design I'm also assuming there's a function pointer that the programmer can provide to us that provides a callback function that is called at the time that we are actually identifying garbage and freeing the block, moving it from being allocated to being deallocated and available to be reused. The final liner function, the name is based on the Java facility for the Java garbage collector, and it just provides the programmer with a way to look at the block one last time. Perhaps there's resources like open file descriptors that are in that block that can be, the file might be closed for an open file descriptor, for instance. It just gives the programmer one last chance to look at the data block before it's actually reused. And of course the programmer might provide null here if there was no need for a finalizer. One thing I'm finessing here is what the units are for the heap size and the block size. So memory allocators might vary. There might be ones that allocate memory at the byte level, so the units for these two parameters would be in terms of bytes, or they might be in terms of words, 32-bit words or 64-bit words. Okay, so right off the bat I can see there's a typo, a handwritten typo on this slide. What I meant here was mem initialize. All right, what's the functionality of mem initialize? Again, I'm given a heap size, and so I probably would use malloc to actually allocate the space for that heap. Malloc is going to return a pointer to a big block, the block that's the size of the heap, and I probably need to set up some control variables inside my allocator to keep track of where the heap is located. So that's maybe a global variable, a hidden global variable that points to the beginning of the heap, and then another hidden global variable that keeps track of the length of the heap. Those would be internal things, not visible to the user. What else would the allocator need to do? Well, it's probably going to maintain block headers where blocks are either allocated blocks or free blocks, available blocks. Why do I need a header? Well, I need to store control information. I need to keep track. Is the block allocated? Is it already been allocated, or is it available to be allocated? I need to know how long each block is. And if it's allocated, I need to know what's the finalizer address to be called when I deallocate this block. And also, if allocated, is the block reachable? We'll call this the mark bit later, and we'll talk about it more when we're talking about garbage collection. Typically I'm going to use single bits for fields, for these two fields, number 1 and number 4. They're just booleans, right? So I just need a single bit to indicate whether a block is allocated and whether a block is reachable. And I can pack that with the block length. But I probably need a separate word for the finalizer address. So you might see a block that looks like this. It'll the block will be preceded by 2 words. I'm assuming here these are 32-bit words, and the length will be in the bottom 30 bits of that 32-bit word, and then I'd have my mark bit and my is allocated Boolean flag in the top 2 bits, and the finalizer address would be in that second word. And then following that is the block contents. So the user, if it was an allocated block, the user would see this portion. These 2 control words would be hidden from the user, but they're there in memory. This is one of the reasons why, one of the reasons why you can have subtle bugs where you destroy those words by mistake, and then your allocator does bizarre things. One thing is, you sit down to implement this sort of stuff, you have to make decisions. Does this length field here, does it include the header, or does it not include the header? Typically, I think in the diagrams I'm going to be using in this session, the length will include the header words. Okay. So let's look at an example here. Have mem initialize. I call it with 1,000. Let's think of it as 1,000 32-bit words. Let's assume these are all 32-bit words here. So mem initialize. My implementation is going to call malloc. It's going to give me a pointer to a block of 1,000 words. Internally, I'll set up some control variables to point to the beginning of the heap and keep track of the length of the heap. And then I'll go ahead and start out. I think the proper way to start out is I have one big block. It's available. That's the first bit here. This bit is really not in use because this bit is just marked as available rather than allocated. Here's the length of the block. It's 1,000 words long, which includes the header. And then I have no finalizer right now because it's not an allocated block. So this is probably what mem initialize would do. It would allocate the memory using malloc, and it would set it up as being one big block that's available to be allocated. Now a mem allocate request comes in. What would happen? Again, a mem allocate request comes in with 2 parameters: how many words to allocate, let's assume, and a finalizer address. And what I would do, again, I'm going to start from the state that's drawn on this slide. Right, here's the initial state when memallocate is called. I need to split off 100 words, or actually 100 words, because that's what the user wants. So I need to actually split off 102 words in order to have the 2 header words. So I would split off 102 words. And again, I guess I'm not being consistent. I said the header would include the length, so let me just correct this. This should be 102. I'll try to do that today. We'll see how consistent I am. So I'd split off 102 words from the 1,000. That leaves 898 down here on a block that's marked as unallocated. Right, that's the remainder that I'm not going to use. I mark this block as being allocated. I clear the mark bit for now. Again, we'll talk more about the mark bit later. And I remember the finalizer address in this second word. Okay, so memallocate would make that kind of operation. Again, in general, after time has proceeded for a while and you've been processing memallocate calls for a while, your memallocate routine might actually have to search through here for a big enough free block to allocate the user's current request from. And there's all sorts of subtleties there. You might need to look for the biggest, you might want to look for the smallest free block that can service the requests in order to maintain as many big blocks as possible in order to satisfy more bigger requests. I'm not going to get into that too much though, because I'm headed towards describing garbage collection. But I need just, what I'm doing right now is just showing you your basic allocator. Okay. One thing in an allocator that you have to deal with usually is alignment. What do I mean by this? Well, aligning values on appropriate memory boundaries is important for correctness on some machines. In other words, some machines you can't read a 4-byte quantity unless it's aligned on a clean 4-byte boundary. And by a clean 4-byte boundary, I mean an address that is evenly divisible by 4. So it's actually some machines where this is mandatory. You won't get the correct value unless the value is aligned. But more often, it's a performance issue. In order to get the best performance out of the system, a multi-byte value should be appropriately aligned in memory. Why is this? It's because the memory system is designed to quickly read aligned values. Typically, 4-byte values like an int or a float on a 32-bit machine should be on a 4-byte boundary, which again, what do I mean by that? I mean the address is evenly divisible by 4. And 8-byte values, like a double, should be on an 8-byte boundary, which again means the address should be evenly divisible by 8. If you're allocating a struct, usually what happens is you assume the worst. You assume the struct might start with a double. So you would make sure to allocate that on an 8-byte boundary, allocate the struct on an 8-byte boundary in case it starts with a double. So what does this actually mean in the allocator? Well, an allocator allocating in units of bytes would probably round up the user's request, the length of the user's request, to be some multiple of 4 or 8. Typically it's going to be a multiple of 8 nowadays. So they waste a little space in order to guarantee a clean alignment. The other side effect of this, of course, is that this alignment ensures that those header words, which in my design are at the beginning of the block, or they immediately precede the block, is one way to think about it. All right, so those will be aligned too. Well, with a memory allocator, you might consider having a mem_free function in your interface, which would require users to call free to explicitly deallocate a block. So this is kind of the malloc free model. But what we want to talk about today is we want to provide an option for people to not use free, and instead, when the heap is full, we run a garbage collector to try to reclaim blocks, identify blocks that can be reused to satisfy the current request for more space. All right, so what is a garbage collector? Well, as I just said, actually, it identifies allocated blocks that the program can no longer reach. Again, what does that mean, no longer reach? Well, it means there's no pointers. No pointers exist in the program to point to that block. If there's no pointers pointing to it, then the program has no way to get to it, to operate on it, so it's effectively garbage. And we can reclaim it and reuse it. And the way we're going to do this is we're going to use what's called a mark and sweep garbage collector. And as you might imagine, mark and sweep has two basic steps. Mark step is define and mark all reachable allocated blocks. This is where that mark bit in the header is used. Right? If we make sure all the blocks have a cleared mark bit, then we can go through and literally mark or flip that bit to a 1, all those blocks that we can reach from the program. When the mark phase is done, then we can sweep over the heap and we can reclaim the unmarked allocated blocks. So we can go over the whole heap and look at each block essentially, and if it's allocated and unmarked, then it's garbage and we can reclaim it. What do I mean by reclaim it? Well, for one, we can call the finalizer function, because this is, again, we've identified a block that can be reused, and we can let the user have a chance to do some final processing of that block before we reuse it. Then we'll mark the block as free, and we really ought to combine it with any adjacent free blocks in order to provide maximal sized free blocks in order to satisfy as big a request as possible. So what would happen is after you get done clearing the allocated bit here, and if I end up with this, if this one's the newly freed one and I end up with 100 words that are free next to another 100 words that are free, I would transform those two blocks into one block of 200 in order to be able to satisfy a request, for instance, of 150. If I got a request for 150, I can't satisfy it with this block or this block, but since they're adjacent, I can bring them together into 200 words. Right? A request for 150 words can't be satisfied by this one or that one, but if I combine the two into a 200 word block, then I can satisfy a request for 150. So typically your garbage collector is going to do that combining or coalescing, it's sometimes called. All right, let me just back up for a moment. One other thing I wanted to emphasize is the sweep. Why does this sweep work? Well, if we look at how we've structured the heap as a series of blocks where there's these header words at the beginning of every block, right? This length tells us how much there is, right? This length tells us how much that is. This length tells us how much this is. So we can skip from block to block using this length field, right? Given this length, we know where the next block starts. Given this length, we know where this next block starts. So we can skip through all the way through all the blocks. Okay, and of course this assumes that we know where the heap begins, as I indicated on my other diagrams, and we know where the heap ends because we know the heap length. So the sweep step is facilitated by these headers. Again, we don't care whether the blocks are allocated or not. We're able to sweep through all the blocks by using the length fields at every step. Okay, so we can sweep through the heap and look for blocks that are marked as allocated and unmarked. Right? If they're unmarked, that means we can't reach them, so they can be flipped from allocated to not allocated, and we can look to reclaim the block and combine it with adjacent free blocks like I showed here. So having those length fields in the header is key to allowing us to do the sweep. But how do we know whether something is reachable or not? Well, there's four ways, I think, that something can be reachable. Right, it might be pointed to by a global variable. So that's one location. We might find a global variable that points to a block. Or it might be pointed to by the stack, by a pointer on the stack. What's on the stack? Remember in our discussion of the Intel machine, local variables are on the stack, parameters are on the stack, temporary values are on the stack, saved registers are on the stack. So if any one of those contains a pointer into the heap, the block that's pointed to is reachable. So that's a second place we can look. A third point to look is in a block that we already know is reachable. So we've identified it as a reachable block because it's presumably pointed to by a global variable or the stack. Then a pointer within a reachable block to another block, the second block, is also reachable. By the way, sometimes we talk about these three, I probably should have put them in a different order, I guess. These three are the roots of the garbage collection. Roots of the garbage collection. these blocks that are reachable, we need to search them again. So the marking procedure is really recursive. Right, I mark a block, then I mark anything that that block points to, and anything that block points to, and so on. What's the base of the recursion? Well, the base recursion is a block. We come to a block, I point it to a block, and that block is already marked. Right, we don't need to scan that block again for other pointers because we've already done it. Okay. Final one, which I really should have included with the first three as part of the roots, is we could have a register that contains a pointer to a block, and that might be the only place the pointer to the block is located. So we need to worry about registers as well. Now most registers will be on the stack, or at least half of them, right? The caller saved will be on the stack because the garbage collector is called when the heap is full. When does that happen? That happens when there's a call to mem allocate and we can't satisfy the request. We go and do a garbage collection to try to identify more memory that's available. So there's been a call to mem allocate, so any caller save register has already been saved, but the callee saved might not be saved into the stack yet. So we need to worry about the callee saved ones. We need to force those callee saved registers onto the stack is typically what you need to do. Make that happen. Okay, so those are the 4 places we have to look when we're doing our marking phase. Let's look at those a little bit more carefully, one at a time. So globals, turns out under Linux, the linker inserts some symbols that we can reference, and the address of those symbols delimit the static data area. And you may remember an earlier lecture where I laid out what memory looks like for a program. Down in low memory, you have the code. Right above that, you have static data, in other words, the global variables. Above that, you have the dynamic data, which means it's malloc areas. And finally, in high memory, growing back down towards low memory, you have the stack. Okay, so it turns out there's these symbols that are thrown into the object code by the linker that indicates where the static data area starts and where it ends. Right, so you can declare these things like I've done here on this slide in your C program, and then you can get their address by taking the ampersand. The result will point to the beginning of the static area, and the result of this one will point to the end of the static area. So that defines one area where we need to scan for pointers. One thing about the global areas, you need to be careful because remember, the allocator has some control variables. In particular, it has something that points to the beginning of the stack, which was the original return value from malloc when we malloc the heap. So let me say that again because I think I said the wrong thing there. But remember, there's some control variables, and let me look for the slide. The allocator is going to keep some control variables. It's going to keep something that points to the beginning of the heap in particular, and this would have been what was returned by malloc when we did mem initialize. It also probably has a length of the heap. The length of the heap is an integer value, so we're not too worried about that. But you do need to worry about heap begin because it's a pointer and it points to the heap. It might make you think this first block is reachable. But what we're concerned about is reachable from the user's code, not from the heap control variables. So you have to be careful as you're scanning over that static global data area. You got to be careful and skip any pointers that you have in your allocator that point to the heap, because we don't care about those. We care about the user's part of the program. Okay. What about the stack area? Well, on the Intel, remember that all the frame pointers are chained together, and we can follow those chains in order to figure out where the beginning of the stack and where the end of the stack is. So if we take the current frame pointer, it points to an old saved frame pointer which points to the prior frame, which again has another old frame pointer that points to the next prior frame, and so on. There's a chain here, or linked list if you will, all the way back until we get to a frame where the saved frame pointer actually is 0. So we can use the initial frame pointer as one delimiter for the stack area that we need to scan for pointers, and then we can use this null word as the end of the area that we need to scan on the stack for pointers. Okay, so we'll need to have some way to get this frame pointer, but you can write a little assembly language routine that can return the frame pointer and then call that from your C program in order to get that. And then from the C program, actually, you can trace back these chains and figure out the bottom, or actually it's the high address where the stack ends. Again, it's a high address because the stack grows this way, right? It grows from high memory down to low memory. So we can identify by that strategy where the stack begins and ends. Okay, what about pointers inside reachable blocks? Well, let's actually run a mark phase. I've drawn a diagram here where I show the roots of the garbage collection being the globals, an area where the global variables are stored, an area where the stack is, and then I've got some allocated blocks here that are linked together in various ways. These are user data structures that have been allocated and connected by the user. So the mark phase would maybe start with the global variables, it doesn't matter. It would be scanning through here for any pointers. It would come out here and mark anything that's reachable by those pointers. And when it marked a block, it would then scan that block for other pointers. Again, it knows the length of the block because it knows there's a header attached to this block that allows it to know the length of the block. So it can scan through here and look for pointers. In this case, there are no pointers to anything in that block. So I come back here and continue scanning the globals, and there's no other pointers from globals. So I'm done scanning the globals. So then I would move on to the stack area. Start scanning the stack area. I'd come down here, I would mark that block as reachable. Again, I would stop then and scan this block for other pointers, but there are no other pointers in that one. So I'd return to scanning the rest of the stack area. Come down here, I'd find this pointer that comes over here and marks this structure. Okay. Then I would stop and scan this one, and this one does have a pointer to here. Okay, so I would then come here and scan this one and identify that this block is reached. I would then scan this block and identify that this block is reached. This block has a pointer to here, but here's the base of the recursion. At this point I say, oh, I've already marked that block, so there's no need to scan that block. And I can then start returning, right? Continue scanning this if there's any other pointers. There are none, so return. Continue scanning this if there's any other pointers. There are none. Return here. Finish scanning this if there's any other pointers. Oh, there is a pointer up here to this record, but oh, it's already marked, so no worries there. Come back down, return, finally return here, and finally return back here and finish marking the stack. At that point then, I'm done processing the roots of the garbage collection, the globals, and the stack. Of course, I really need to look in those in the callee saved registers, but I think in my world, I would have pushed those callee registers out of the stack before I scan this area. Okay. Now, the question is still, what is the garbage? I've marked everything that in fact is not garbage. So I would do a sweep now through the heap, looking at all the allocated blocks and marking anything that's identifying anything that's not marked as garbage. So this block is allocated because I drew it in the diagram. That's how I'm identifying allocated blocks, by just drawing them. So, but it's garbage because it's not marked. This one is garbage because it's not marked. This one is garbage because it's not marked. Okay, and the program would then call the finalizer and also try to combine these blocks with any adjacent free blocks to make maximally sized free blocks. One other thing I need to remember to do when I'm doing my mark and my sweep, probably as a side effect of doing the sweep phase, I need to reset the mark phase so that I'm ready to do a garbage collection again in the future. All right. Now, this is actually what I've identified here is actually conservative garbage collection. What do I mean by that? Well, Java garbage collector actually has runtime type information available to it, so it knows exactly where the pointers are. So it can distinguish words in memory as to whether they're pointers or integers or floats or doubles or whatever. So it knows exactly what pointers are. It can do exact garbage collection in that context. But if we're doing an allocator in C, we don't have runtime type information available to us. And in fact, C's got things like unions where we have no way, even with the runtime type, to know what's in a particular bit field at a particular time. So we have to do something that's not exact, but is labeled conservative. What does that mean? It means that the bits that look like a pointer, if we're looking at a word and the bits look like a pointer into the heap, then we have to assume it is a pointer into the heap. So again, in green here I've drawn a heap. I have a control variable that tells me where the heap begins. I know how long the heap is. And I'm looking at some word in memory somewhere, maybe in the globals area, maybe in the stack area, maybe inside a block that I know is already reachable. And I just interpret those bits as if they were a pointer because I'm not sure. But to be safe, I better assume it could be a pointer. And I look at those bits as a pointer and I see, does it point into the range of the, if interpreted as a pointer, does it point into the heap? If it does, I assume, I don't have any choice really, I assume it is a pointer and I go ahead and mark the block at that position if the block is allocated. Again, if it points to an unallocated block, then I know it's not really a pointer, it just looks like a pointer. Because the point is I'm forcing an interpretation on a set of bits, don't know for sure, it might actually be an int or a float, right? Those bits, by chance, the int value or the float value might by chance contain a value that looks like it could be a pointer. I don't know for sure, but to be safe, to be conservative, I will assume it does point. And I will go ahead and mark an allocated block that it points to. Again, this is conservative because it might mark a block that does not need to be marked. Right? I may interpret an integer mistakenly as a pointer just to be safe, and I might overmark. But it's okay to overmark. Right? That's just a heap utilization issue. I may waste some space that way. But it's definitely not okay to undermark, right? If I don't mark a block that is in fact in use, then it becomes a correctness issue. Now the user's program is probably not going to work because I'm going to reallocate that block to be something else, and now the programmer's got two data structures in the same memory, and that's rarely a good thing. So I have to be conservative here, and I'm going to, the cost of being conservative is I might overmark and I might not utilize the heap quite as well as I could if I had exact runtime type information. Okay. Well, that's a whirlwind tour of basic garbage collection, but just be aware, again, there's lots of advanced topics. If you actually look at the Java garbage collector in detail, you'll see it's doing a lot more than what I'm just laid out for you. I just laid out for you the basics of garbage collection. There's lots of advanced topics that you'll see in garbage collectors. For instance, a garbage collector might be concurrent. It might be running at the same time as the user program is running. It might also be incremental. It might not wait. It might, because it's both concurrent and incremental, for instance. It might be, well, they don't have to be both. It could be incremental. Every time you allocate, it could do a little bit more. Every time you call mem allocate, the garbage collector could look around and do a little bit of the garbage collection marking, for instance. This is just to amortize the garbage collection time over all allocators rather than having quick allocation for a long time and then when you run out of memory you have a big delay while we do garbage collection. So, again, incremental is one approach to that. Concurrent is another approach. You try to do garbage collection at the same time the user's program is running. Another advanced technique is generational garbage collection. A lot of stuff you realize is going to be there for the lifetime of the program. It's always going to be there, so we try to put that in a spot in the heap where we don't look at it over and over again every time we're doing garbage collection, because we determine that it's never going to move. Let's not waste our time looking at it when we're doing garbage collection in the future. There's a great online resource if you're interested in learning more about these more advanced topics. It's called the Garbage Collection Page, and it's maintained by Richard Jones, who's also written a couple very good books about garbage collection that I would recommend, again, if you're interested in more advanced topics. All right, let's stop there.